Okay, I think we can slowly restart. So for the hands-on, we will have, it's a bit special, we will have two hands-on sessions. First on Phonon-assisted optic by Emmanouil Kioupakis. So there will be first a short intro, and then there will be a hands-on session. And then at, let's say 10:30, something like that, 10:35, we will have the second hands-on on the superconducting properties given by Roxana, and then again followed by a hands-on. So Manos, the floor is yours.
Oh, thank you very much, Samuel. So what I'd like to discuss with you today is how to do a Phonon-assisted optical calculation in practice, how to use the code, what are the main keywords, and what are some tips that you could use on how to do the calculation. So this tutorial was prepared in collaboration with Zhao Zhang, who will be able to help you during the hands-on sessions, as well as Kyle Bush, who will give you hands-on support. So for now, we're just going to run through a simple example for silicon, and then I'll stay around to help answer any questions you may have about how you can use this in practice for your projects. All right, so just a reminder first about what we're trying to calculate. So let's look at the top equation here. This equation gives us the imaginary part of the electric function, which describes the photon absorption, phonon-assisted photon absorption by a material, particularly in the spectral region between the indirect and direct bandgaps. What are the ingredients? So constant prefactors, 8 pi square, e square, volume of the unit cell, photon frequencies, so photon frequencies, and then a sum over bands, initial and final states, energy conserving delta function, and the matrix elements. And for the matrix elements themselves, these generalized matrix elements, S1 and S2, the ingredients are the velocity matrix elements that describe the optics, the electron-phonon capital matrix elements G that describe electron-phonon scattering, and again, energies of your electrons and holes in the material. Okay, I also have these imaginary gammas, these broadenings, that actually help us avoid divergences in the spectra because you're dividing by an energy difference here. So that energy difference can become zero. And we'll discuss the case that when it becomes zero and what you could do to avoid it. All right, so if these are the ingredients, and again, the two paths S1 and S2 correspond to the two different orders that optical absorption phonon-assisted optical absorption can take place. Either you absorb first the photon, followed by scattering by the phonon, or first you get momentum by the phonon, followed by the light absorption. And last but not least, we also have to account for the occupation numbers. You always need to ensure that you go from occupied to empty states, but also that you account for phonon absorption and phonon emission. And for every case, we need to look at absorbing a phonon. So you need to have a phonon, you need to go from an occupied to an empty state, and you also need to subtract the opposite process because the net rate is the rate of going up minus the rate of going down, and then similar for phonon emission. All right, so how does this go in practice? Right, this is what we learn in textbooks. How do we go to practice? The first thing we do is we approximate the delta function by a smooth function, right, like a Gaussian or a Lorentzian. And the code right now does both. The default one is the Gaussian, but it also outputs files that contains the Lorentzian broadening. How do you control the broadening parameter? It's the dE Gauss variable that you see here, dE Gauss W. Okay, so the way you start is you set it to the resolution you want. Say you want the spectra with a resolution of say 0.1 eV. And then what you do is you increase the K in the Q grids until the spectra stop changing, until you reach convergence. So that's the first thing you need to decide. What's the resolution you want in your spectra? The other thing you need to decide is whether you want to go with the DFT eigenvalues that come out from the code along with your linearization, or whether you want to replace them from another file. For example, if you have done a GW calculation, or say you have applied a correction to your eigenvalues, then you would do an I grid equals true. And you need to provide a file that contains that. And many codes output it, like the Berkeley GW code will create these files for you if you want to do your GW calculations this way. But in general, it's the same format as the eigenvalues that Wanye outputs, except you use the different ones. All right. So these are the first things we do. We broaden the Gaussian. We decide whether we want to read eigenvalues or not. And then how they work in practice. The first steps, as with every calculation that relates to EPW, is we create the Guagnet functions and we express all the quantities in the Guagnet basis, the energies, the optical matrix elements, and the Phonon-assisted electron-Phonon coupling matrix elements. And when we start, we're ready to interpolate, and that's when the action happens, right? So the first step, the creating Guagnet base, is the same for all calculations. The second step now is where you decide to do the optics. So the first flag is the logical flag for indirect absorption, which is equal to true, and that will call the subroutine for Phonon-assisted optics. That's the first thing you need to do. The second thing is you have two choices with regards to the grids. Either you can use your K and Q points to be on the full grid, which is what the right thing to do, or you can exploit symmetries and reduce one of the grids, in this case, the K grid for the initial state of the electrons, to the reducible wedge. You can do it. However, you need to be careful because the property you are calculating, the spectra, are a vector quantity, right? I forgot to mention here that this will be the spectra along, oh, sorry for the symbol here. The lowercase e is the unitary vector, that is the polarization of your light. And so the quantity you'll get here depends on the polarization, whether light is polarized along the X or Y or the Z direction. Okay, so that's something you need to be careful about. It's a vector. So when you use symmetry, you've asked the code to use an irreducible wedge, but now the reducible wedge breaks the symmetry because all of a sudden it's asymmetric towards one direction. It's okay for scalar quantities, but for vector quantities, you need to apply symmetry rules. So the code as it is right now does not apply the symmetries in order to properly rotate the spectra and give you the spectrum for your full crystal. But in the simple case of a cubic crystal like silicon, the solution is very simple. All you have to do is average the spectra that come out along the three directions. So now, again, I would emphasize, only because we use an irreducible wedge, the spectra along the X, Y, and Z direction are not the same with each other, right? When you do a quantity like the total energy, which is scalar, that's not a problem because that's depend on the direction. It is a problem though for a vector quantity or any tensor quantity for that matter. Okay. So cubic crystals don't have directional dependence, whether light is polarized along X or Y or Z or any direction, there's only one spectrum and you will get it by average the three. Alternatively, you can set the mesh to false. In this case, you do the full grid. You won't have to worry about symmetries or about symmetrizing the matrices in the end, but it will take a lot longer to do. All right. In the case of silicon, the reducible wedge is only 1/48 of the full zone. So your calculation would be 48 times slower to arrive at the same answer. So it's up to you to choose which way to go. But in our example, we will use the reducible wedge and then we will average out. All right. So that's one choice you need to make early on. The other choice is you need to decide what is the spectral region that you want to calculate the spectra for. So in this case, we'll start from 0, go to maximum, so that's omega min, omega max, and how many steps you want along the way. Do you want 100 points, 1,000 points? It's a small difference to add more. All right. So in general, we want to look at the Phonon-assisted spectra in the region between the indirect gap and the direct gap. In the case of silicon, around 1.1 eV all the way to 3 eV. At 3.4, that's where the direct gap, that the direct absorption sets in, and that we describe with a different formalism. All right, so so this is how you decide the spectral region. So the code will only try to do the calculation for these specific photon energies. And last but not least is another trick that you can use to save time. Right, so you have many bands in the calculation. That's something I also want to mention as well. In the case of indirect absorption, you have your electrons absorbing energy that's on the scale of several EVs. So the states that are involved are not just only those few thermally occupied states around the Fermi level. You're talking about states that are several EVs away from the Fermi level, right? So you'll be sampling a large fraction of the Brillouin zone in the case of silicon. So there'll be many bands involved, many K vectors, and we want to minimize as much as possible. And the way to do this is by setting a window, right? We call it the Fermi energy and the Fermi window, but not just because we use the same variables in the other parts of the code, the transport and conductivity parts, but here it's not truly a Fermi level. Here it acts solely as a window that helps us truncate the states. Okay, so the code will only consider states that start or end within this window you specify. You specify the middle of the window, that's what we call the Fermi energy, and you specify the thickness of the window around which you will calculate the absorption. So, for example, in the case of silicon and photons energy up to 3 eV, if your initial state is down at say -4 eV, and if you absorb 3 eV, you still have the valence band. Those electrons at -4 eV will not absorb any light. So they don't need to be in the picture. So you can safely start from a higher energy relatively. All right. How wide should the window be? The window needs to be, of course, wider than your highest photon energy that you're looking for. Say if my photons go up to 3 eV, I definitely need to go consider states all the way down to 3 eV. But also need to consider that my electrons may also absorb a phonon. So I need to add the highest possible phonon frequency. Most materials, it's about 100 millieV, like 0.1 eV. If you have hydrogen, it may go up to say 0.3 eV, but usually it's a fraction of an eV. And the other thing is that even though you may have states which are further outside your window, you are using Gaussian broadening. So even states outside the window have a tail that may contribute into your spectral region. So I would say if you go 5 times the Gaussian width, at 5 times Gaussian width, the Gaussian function is decayed quite rapidly. So that is a safe window to use in order to calculate your spectra. Okay, omega max plus the highest phonons plus a number 5 or 6 times your Gaussian broadening. That's a safe window to use to ensure that there's no states that you are missing out that contribute to your spectral region. Okay, so that's a few tricks to consider, and some other practical tips in practice. Again, we mentioned that you have states that could be your electrons may start or end at states which are very far from the band extrema. Okay, as far as the photon energy you are asking to calculate, in this case 3 eV. So you need to ensure that you have all the one-year functions you need to reproduce the band structure for the energies where photons can take the electrons, or they can take them from, or they can take them to. Okay, so just to ensure that you have a good band structure throughout your Brillouin zone and for all the energy that your carriers may be excited to. Okay, and you're also summing over intermediate states. So that's another thing. You also need to consider that not only you need to have your states accurate within your window, your initial and final states, but also the intermediate states that you are summing over can be further out in energy, can be at 10 EVs away. So again, something you need to consider that you are taking into account properly, that you don't have any spurious artifacts coming from poor linearization for those high energy states. Another thing is that what grids do you need to converge? The grids that you need to converge, they are not as fine as the grids you need for transport. Like you don't have to go to say 100 by 100 by 100 grids in most cases, but you still need to go to reasonably fine grids, like maybe 20 by 20 by 20 or so. How is that controlled? It's controlled by the density of states, right? So the same grids that give you a smooth density of states for your energy resolution, the Gauss, they'll be the similar grids that the ones you will need for Phonon-assisted optics. And just a quick rule here, like look at the conduction band of silicon, right? The index gap is around at 1.2 eV from the valence band maximum. The delta gap is around 3 eV. So the bandwidth here is about 2 eV, 2 electron volts is the energy difference between this point and that point. So I have about 2 EVs. If I now want an energy resolution of say 0.1 eV, that means I have at least 20 Gaussian widths between my minimum of this band and the maximum of this band, which tells me that if I want to get a resolution of 0.1 eV for this band of 2 eV, I need to take at least 20 points. So my grid needs to be on the order of 20 by 20 by 20 or 40 by 40 by 40 in order to ensure convergence. So that's a quick rule to estimate how many points should you aim to go to, what should your fine grid be in order to reach convergence. And last but not least, the imaginary denominator. The code right now does not let you choose the variable, but it has a table of 9 possible values that it chooses by default. Okay, so the code will calculate all 9 spectra for these 9 values. What you need to see is that your spectra should not depend strongly on what is the value of this imaginary broadening. It's a numerical parameter here that is meant to avoid the divergence. If you do see, however, your spectra are very sensitive parameter, you have a problem. The problem is that second-order perturbation theory breaks down in that case. The problem is that you have a divergence because the denominators you see here become 0, right? The broadening is a small number, so only if the first term here is 0, that's when the broadening matters. When is this 0? It is only possible when an intermediate state becomes resonant with the initial state plus the photon, which is true only when you have direct absorption becomes possible. For example, if your initial state plus the photon is equal to intermediate state, well, that's not really a virtual intermediate state, that is a real intermediate state. Your photon can take you to that state. So in that situation, you have direct absorption. And that's an issue that creates a problem for this formalism. So you want to stay away from regions where you do have direct absorption, because otherwise you may have these divergences that depend on the broadening. What can you do in that case? You can use a broadening calculated from the Phonon self-energy, because that broadening is a real quantity, right? It's like the lifetime of the intermediate state. So you can either calculate it, or you can use a series of broadenings and kind of extrapolate for what would the value be if you were to take the broadening independent term. And I'll be happy to tell you more about how to do this trick in practice if you're interested in calculating Phonon-assisted spectra in a region where direct transitions are possible. Okay, so if you do things along these lines, you would get spectra for silicon that look like this once you converge them. Now, in this case, we have limited ourselves to a very narrow energy window. You see omega min and omega max are very small, just a window of 0.4 eV. And in this case, we can go to very fine K and Q grids to resolve these discontinuities and steps from the Phonon-assisted absorption, the Phonon absorption and Phonon emission term. And also, if you go to broader spectra, you get the absorption for the whole visible range. And here you have transitions throughout the Brillouin zone. So the spectra you need here are much, much coarser that you need to converge. Well, I see some questions in the chat, so I'll want to take a quick look. Oh, I see the question about our mobilities. So yeah, this is a very short presentation, but if everybody is ready, we can go. If you have questions, I'll be happy to answer them. Otherwise, we can go straight ahead and look at the practical problems. So please, I will upload these slides on the course website as well, so you'll be able to find them later today. But in the meantime, please download the sheet and we can start from that to do the calculation, right? So, and if you are logging on Frontera, you should be able to